Okay, let us discuss the next problem. So this is problem number 2.20, something related to rotating horizontal cylinder. Now this question says a horizontal cylinder closed from one end is rotated with a constant angular velocity omega about a vertical axis passing through the open end of the cylinder. So we have a horizontal cylinder. So let us say this is the cylinder we have. Now this side, one side is open, this side is open, and this side is closed. Now the cylinder is rotated through a axis passing through the open side. So this is the open side, and this cylinder is rotated with angular velocity omega, an axis that passes through the open end. Open end, let me write again. This says the outside air pressure is equals to P naught. So there is a pressure, outside pressure is P naught. So P naught is basically outside pressure. So you can see P naught is outside pressure that is given to you. Are you getting? I think all of you have copied this one. Molar mass of air is m. M is also given to you, that is molar mass. So mass of 1 mole of gas. So molar mass of air. So this cylinder contains air. And the molar mass of air is m, capital M. Find the air pressure as a function of distance r from the rotation axis. So we have to find pressure as a function of r, and r is measured from the rotation axis. So this distance r. So we have to find pressure as a function of distance r. So what my target is, if distance from rotation axis r, what is the pressure at this point? So on this line, what is the pressure? So we want to find out the pressure at this point. The molar mass is assumed to be independent of r. One more thing is given. This is constant. This is nothing to do with the r. Here also molar mass is m. Here also molar. So molar mass is constant. That is capital M. Now how will you proceed this problem? So you see, let us try to visualize this one. If you just rotate this one, so if you rotate this horizontal cylinder, you see the air will go towards this side. So closed end will have, so you see this side will have more air. Are you getting or not? And this side will have less. So this side you have dense, this side you have less dense. Are you getting? So air will basically press. You can also think this side will have higher pressure, this side will have lower pressure. One more thing, when distance r is equals to 0, pressure is equals to P naught, because this end is open to atmosphere. So we have one boundary condition. When r is 0, pressure is basically equals to P naught. So one can expect pressure goes increasing if you increase the r. So this means if r increases, pressure increases. Let us consider the equilibrium of a small x, a small part of the air. So this is my cylinder. This is the vertical axis. Let us say at a distance x, I consider a air column of thickness dx. So I am considering a air column of thickness dx. You see, pressure gets increased. So let us say at this point pressure is P. So this column, this surface, this cross section pressure is P, but here you will have higher pressure. So let us say at this cross section pressure is P plus dP. Are you getting? So what I want to say, when x is equals to x, pressure is equals to P. But when x is equals to x plus dx, pressure gets increased. So pressure is P plus dP. So you see, slowly pressure gets increased. X is increasing, pressure is also increasing. So R is increasing, pressure is increasing. Now if I consider the equilibrium of this column, So what are the forces that is acting? So this is the air column we have. From this side you will have a force that is P plus dP into area of the cylinder. From this side you will have a pressure that is force P into area. Now there is no friction between this cylinder and the air column, so there is no force acting on this line. There is no force acting on the bottom surface also. Now this air column is basically moving in a circle, you see. So this is moving in a circular path. So this air column is moving in a circular path. So now I can apply total force towards the center is equals to mass into acceleration. So total force, now I will write equation in the radial direction. So force towards the center is equals to mass into acceleration towards the center. So force towards the center is P plus dP into area, that is the towards the center, minus pressure into area, that is away from the center, is equals to mass. So let us find mass. Is equals to mass into acceleration, and or acceleration is m omega square. So let us say m omega square r, and r is x in this case. I have to find mass. So how we will find mass? So let us say this is area is A and this is dx, so volume is A into dx. So I can say, so let us skip this equation as it is. Now let us say volume will be, a small volume will be A into dx. I have to find mass. Now I can apply Pm is equals to dRt. So Pm is equals to dRt. You're getting? So from this equation density will be given as Pm by RT. So D for density, P for pressure, M for molecular weight, R is the gas constant and T is the temperature. In this question temperature is also given to you. So temperature is given. So let us say atmospheric temperature is given to you. So let me write here initially also. So temperature of the atmosphere is given. So T is given, temperature of atmosphere. That is given to you. And there is everywhere there is the same temperature. So you have either you have here, here or here. So this point, this point, or this point, or this point, or this point, you have the same temperature T. So now I know the density, I know the volume. If I multiply by density into volume, I will get mass. So small mass dm will be, density is Pm by RT into volume you have. So volume is A into dx. So you will get dm. That's the mass of the small part. Now if I write equation that is P, so let us plug the value of m in this equation. That is basically dm. If you want you can write dm here. The mass is very small, so let us say dm. So you will have P plus dP minus P, so dP into A. So here you will have right side, left side dP into area is equals to dm is this value, Pm by RT into A into dx. This is your dm, and dm multiplied by A into, so dm multiplied by omega square x. So you see here, so this is dm multiplied by omega square x. So I multiply this by omega square x. Now things are very easy. A goes out, so I will have dP by P is equals to omega square m RT x dx. Now I have to integrate this equation. I have already said when x is equals to 0, pressure is P naught. Let us say when x is equals to R, pressure is P. So this side if I integrate, I will have ln P by P naught is equals to omega square m omega square RT, and this is x square by 2. So 0 to x, so simply r square by 2. Are you getting? So I can write P by P naught, this is equals to e to the power m omega square r square by 2RT. So pressure will be P naught e to the power m omega square r square by 2RT. So this will be the pressure. Are you getting? So you see pressure varies exponentially. So if you increase R, pressure increases. One can draw the diagram, one can basically draw the graph for R versus P. When R is 0, pressure is P naught. So when R is 0, pressure is P naught. And after that, pressure varies exponentially. So you will have something kind of this kind of function. So this is P naught e to the power m omega square r square by 2RT. So exponential variation of pressure. Are you getting? Let us copy this one fast and then I can go for the next problem. These problems are easy problems. You have to consider so one important point in this question you have. From the idea, from a daily life idea, you think if you just rotate a tube, the other end of the tube, that the closed end will have higher pressure, open end will have lower pressure. That's the first idea. You should have this common sense. And once you have this common sense, at a distance x you can assume pressure P, and x plus dx you can assume pressure P plus dP, because pressure is increasing. And now next you have to assume, you have to think that the small part dm that is moving in a circle. Now you have to write the circular motion equation, that is PV, circular force towards the center is equals to mass into acceleration. Now another important part you have to how to find the mass. Mass will be volume into density. And density you see we'll find using Pm is equals to dRT. One important part you see in this question, density is not constant. If you see density, this is given by this equation. You see density is function of pressure. You see at this point you have higher pressure, so density is even higher. That is very logical. If you rotating this one, this side will have more air particle, this side will have less air particle, so density will be higher. So to find out the mass, I have to again consider the pressure, because density is a function of pressure. So that's why I have to integrate this term. So when I am integrating, the pressure will come again because of this mass, because mass itself varies with the pressure. Are you getting or not? So this is a horizontal cylinder rotating, and we have to find out the pressure as a function of x, pressure as a function of r. We'll do the same kind of question again. There are many questions of this kind in which we consider the equilibrium of a small mass dm, and we see what the force is acting, what is the motion of that a small part dm. We'll discuss the next problem. I think all of you have copied this one.